Okay. So today we're going to learn about rational functions, and we've seen them before this year. We just don't know how to actually make them yet. So today we're going to go through all of the little steps of how to come up with all of these different things we have to find. So up here we have just some examples of rational graphs. They're kind of characterized by their asymptotes. It's like the most famous thing that people think about. And it's like, oh, those are the ones with the asymptotes. Yeah, there's vertical asymptotes. There's also horizontal ones we're going to learn about today. So this one right here on the left is a special one. It's called our apparent function. So you should remember that from Algebra 2. It's the most basic rational graph, 1 over x. What does rational mean, the word rational? Do I say it? John, what did you say? It's a fraction. Rational means fraction. It's any number that can be written as a fraction. We learned that earlier this year. So you can see here, these are all fractional, rational, with variables in the denominator. There's always an x in the denominator. So you can kind of just see a few more examples. The larger it gets, the weirder the graph gets. So can you see how this one actually has a quadratic on the bottom? And then what do you kind of see up here? Yeah, it's kind of like that quadratic type shape. So there can be all kinds of stuff thrown into these, and it just kind of gets weirder and weirder as we go. But let's first talk about the domain, which we should be professionals at by now because we've done so many of these, and we just did one for our warm-up. So the way you find the domain, it's the values that would cause the denominator to be 0. So we always start with all real numbers. It's everything but the 1 or 2 or sometimes 3 values that cause the denominator to cancel out. So what's the one problem for this one?
3.
Number 3. Because 3 minus 3 is 0. And then Tanner, we have 0 in the denominator, and that's not good. So x can definitely not equal 3. So remember, the domain is the left and right space that the graph takes up. That's basically telling me that the graph doesn't take place at 3. And why do you think that is? What do you think is at 3? Yeah, there's an asymptote there. So we'll get more into this in a second, but basically this is telling me it's like a force field right there. And this graph cannot cross a vertical asymptote. So we basically just have like this empty gap where there is no x value. There is no value of 3 ever. This one over here is kind of like our warm-up. We have to factor it first. So what factors of -5 add up to -4? Good. -5 plus 1. Now this one actually has a factor that would cancel, right? We'll talk about that in a second. But before we cancel, we have to come up with our domain. So once again, it's all real numbers. But x cannot equal -1 and +5. And the two values that would cause there to be 0 in the denominator.
So you don't simplify?
We will in a second, but before, to do the domain, you do not simplify. We will in just a second, though that means something else. All right, so let's take a look here. We have a new concept, and it's called a hole in the graph. Literally. Sometimes there's a hole in the graph. Basically, when you throw all these functions and weird x's and squares into like one graph, sometimes things just like cancel out weird, or something weird happens, and there's literally just nothing there. Okay. So the way that we find out if there's a hole is if the factor cancels. Tanner, stand up if you need to. It's an asymptote if it does not cancel. So basically what we're going to do, we're going to take our domain and we're going to split it into either asymptotes or holes. It's one or the other. There's a reason that there's no x value there. Sometimes it's a hole, sometimes it's a vertical asymptote.
So -5, that factor would be a hole for the cancel.
Correct. The solution, x equals 5, would be a hole, and the other one would be an asymptote because it didn't cancel. So we'll do a few of those here, and actually we're going to do those exact same examples. And it just kind of gives you the definition of an asymptote, which we already kind of know. It's a line in which the graph converges. What does converge mean? Do what?
Cross.
Sometimes, yeah, kind of. I like to think of the word approaches. So like it's a line that the graph approaches. Now sometimes it will never cross a vertical asymptote, but it will sometimes cross a horizontal one. We'll see that here in a minute, but it still kind of approaches it and stays next to it. So now let's just do, sorry. Oh yeah, from the ones above. So these are the ones we just did. So let's identify. So just a second ago we said the domain was all real numbers, but x not equal what? 3. Positive 3. So does x minus 3 cancel for this one? No, it does not cancel, so that means that value is a asymptote. And it's always x equals, it's a vertical line. So we will say there is a vertical asymptote at x equals 3. The asymptote is at 3. That's why our graph cannot equal 3. Does that make sense? We're basically saying that why it cannot equal that number. Well, because there's a force field right there at x equals 3. Now our other one over here had all real numbers. What was it? X cannot equal -1 and +5. We need to split those two numbers into wholes or asymptotes. So which one canceled? The 5. If it cancels, that means there was a hole. So I would say there is a hole in the graph at x equals 5. And the other one did not cancel, which means it was a vertical asymptote at x equals -1. So we start with the domain, that's everything. We then split the domain into wholes or vertical asymptotes. Okay, do all of the above on this one. Domain, wholes, vertical asymptotes. Figure out all 3 of them. So this would be x plus 2, x minus 2, the difference of squares, right? So domain would be all real numbers, but x cannot equal 2 and -2. Does anything cancel? No, you have to have the entire factor to cancel. I cannot cancel an x with an x because this x is tied to a 2 with a plus sign. You can't undo addition with division. That doesn't undo addition. So nothing cancels, so therefore we have vertical asymptotes at x equals 2 and x equals -2. And I would write it out twice because it is 2 different vertical lines. Just write it the equation of a vertical line. Now you can actually graph this and kind of see, you can see what's happening. So get out your calculator because I want to show you something. Go to y equals. Did I ever show you like the little Nintendo cheat code, like the arrow thing to do a fraction?
No.
Do math right up. And what do you think n over d is talking about? Numerator over denominator. So hit enter, and it puts little boxes in. So you can just type it as a fraction. Super handy. You don't have to worry about parentheses or anything like that. So then type in x squared minus 4 on the bottom. X over x squared minus 4. And you can see this rational graph. You see both of those vertical asymptotes at 2 and -2. Alrighty. The next thing we need to figure out is x intercepts. Okay. Now this says we find the x-intercepts by first of all simplifying. It has to be in lowest terms, so we will cancel, and then the solutions are the numerator set equal to 0, whatever that comes out to. Okay. So let's start with this one right here. How would this denominator factor
X plus 1, X minus 1.
Just for practice, let's do everything we've done so far. So what would the range, or sorry, the domain be?
All numbers except x can equal 1 and x can equal
Good. All real numbers, x cannot equal -1 or 1. Now this can be confusing because you have to remember which factor the solution came from, because one of them does cancel and they're both 1 and -1. So which of these factors would cancel for this one? The x plus 1, which is actually which solution? The -1. So we have a hole at x equals -1 because the x plus 1 factor canceled. Which means that we have a vertical asymptote at x equals +1. I'll show you this on the graph here in a second.
No.
The x plus 1 factor canceled.
Right.
The solution that came from +1 is -1.
So you said x plus 1 is 0.
Oh, and X
No, and-
equals.
Yeah, x equals -1 is actually the factor that canceled, so the one that cancels as a whole. So the way I remember it is it cancels and leaves a hole in the function. I don't know. That's the best I got. But the one that canceled is the hole. So now the whole point of this is to come up with the x-intercepts, but it has to be in simplified terms. So I'm going to rewrite this as the only thing left on top over the only thing left on bottom. And what it says to do is take the p of x, which is the numerator, and we set the numerator equal to 0 and solve whatever it comes out to be. So in this case, pretty easy. X would equal 2. Add 1 over, or sorry, add 2 over, you get x equals 2. Now I always like to write x-intercepts as points so we don't get confused with all these x equals and y equals and all these crazy things going on. So what is an x-intercept of 2 written as?
2, 0.
Over 2 up 0. So write it as a point 2, 0.
I spaced out whenever you were talking about how to go there.
Set the numerator equal to 0 after you cancel.
Just
So now, you don't have to do this, but look up here at least. Let's graph the original function. So I'll type it in. Oh, sorry, I'll do math right up, do my little cheat code to insert a fraction. And then I'll go ahead and insert x plus 1, x minus 2, all over x squared minus 1. Graph. Does everyone see, let's see if we can see all of these things. Does everyone see the vertical asymptote at 1? Yep, it's right here, right? +1. Now, the hole is kind of hard to see, but I will tell you, you can always trace that x value. Where's the hole at? So type in -1, and it'll put x equals -1. And if you hit enter, it will give you the output, the input-output, the y value. So hit enter. What is y? No? Nothing. There's blank. There's nothing there. It's a hole. So that's how you can kind of verify and see if your hole is actually there. And then, can you see the x-intercept? We said it was 2. Can you all see where it crosses the x-axis right there at 2? So we can definitely see all of those things that we just found. Okay, so take a second and do t of x on your own. Did anything cancel?
No.
Nope, no holes. So domain, vertical asymptotes. The x-intercepts are the numerator set equal to 0. So 2x plus 1 equals 0. Subtract over 1. Divide by 2. That means x equals -1/2. And let's go ahead and write it as a point. So I have an x-intercept at the point -1/2, 0. So Christmassy.
Looks great.
If the degrees are the same, the horizontal asymptote is at the ratio, meaning division, of the leading coefficients. What is a coefficient?
The number
Number
of
of
x.
Good. The number in front of the largest x exponent in standard form. So let's take a look at r of x. Which scenario is this? Is the denominator larger or are they the same? Yeah, the degree of the numerator is 1, x to the first power. The degree of the denominator is a 2. So if that's the case, what's my answer? Y equals 0. That is a horizontal asymptote. So you can do HA. Basically what that looks like is it's a horizontal line at y equals 0, just like so. Now a graph can cross a horizontal asymptote. Okay, we'll get to that next class. But basically what the horizontal asymptote tells us is where the graph goes as it goes off into the sunset. The end behavior, basically. So sometimes you'll see a graph, it'll just kind of come up, it'll approach it, and then it'll just kind of skim underneath the horizontal asymptote. Sometimes that happens. The other possibility is it will actually cross it. So sometimes you'll see a graph cross a horizontal asymptote, but then it'll come back down and kind of skim across the top. So it's either going to skim across the bottom or the top, but you will see occasionally it will cross a horizontal asymptote. The one you cannot cross is the vertical asymptote. That's the horseshoe. Okay? So let's take a look at g of x. Which scenario is that? Larger or the same?
Okay.
The same. So that tells us to divide the leading coefficients, and that's my answer. So what is 8 divided by 4? 2. Now write it as a horizontal line, y equals 2. So what that looks like, there's literally a horizontal line up 2. And then the graph either kind of skims across the bottom of it, or it will cross it and kind of come back down. I don't know how. And there is one more possibility, but we're gonna not do it. You're welcome. There is a scenario in which we can actually have something called a slant or oblique asymptote. So I want you to know what it is, but we're not going to deal with any that have this. But basically, it's an asymptote that's a kind of a diagonal line, it's slanted, and the graph will basically come up and approach it that way. It'll kind of skim up at a diagonal. So that happens. Sometimes be aware of it, but we won't have to find that. All right, so let's do all of the above for this one right here. Go ahead and take a second and do everything we've done so far for this problem. Do it. Because there's a hole there. There can't be an x-intercept if there's a hole, right? So we get rid of the holes first. We figure out where the holes are. So if there's no x-intercept there if there's a hole in the graph. So we always do x-intercepts after we find the holes, right? That makes sense? And then there's nothing to solve for here. There's no more x's on top. So if I set 1 equal to 0, that doesn't make any sense. So there's no x-intercepts. And then the last thing, the horizontal asymptote, the degree on the bottom is larger. So what is my answer?
Oh, hard. Not. What?
So here we can see our graph. Do we see the vertical asymptote at 4? Yeah. How can I check and see if the hole is correct? What did I push? How do I plug it in? Trace. Trace -4. And it says y is blank. So we're good there. There are no x-intercepts. So basically that's telling me it's not crossing my horizontal asymptote, right? If the horizontal asymptote's there at 0, it's not going to cross it. Okay? And there's no x-intercepts yet. We talked about that. So everything we talked about was right. How do you find the y-intercept of any graph ever? Perfect. We'll plug in 0 for all of the x's, right? Substitute it in. So x is 0, x is 0, cancel, cancel. What am I left with? 4 over -16, but we can simplify that to -1 over 4. And remember, a y-intercept is over 0, down 1/4. So that's just another piece to the puzzle that we can graph to make our graph a little bit more accurate. So that is not any different than anything we've done. Okay, last one for today. Go ahead and do r of x on your own. So here are your answers to r of x. So I just copy that top left corner. Now there's a lot. Can you see how there's a lot going on right here? We're not real sure what's happening. So I'm going to show you one more thing. I usually show my algebra twos, but some teachers don't. It's something called zoom box. So if you hit zoom box, enter. Can you see how it gives me a little cursor, a little plus sign? You'll want to move that to the top left portion or top left section of what you want to zoom into. Now wait a second, because so you can see how it works. If you hit enter, your plus sign turns into a little box. And what it allows you to do is it actually allows you to drag a rectangle around what you want to zoom into. So I'm going to kind of drag my rectangle around this x-axis interceptee area to see what's really going on down here. And then hit enter, and it zooms into that rectangle. So now hopefully we can connect our dots a little bit better. So can you see how it comes from the top? See where it hits the x-intercept? And then if we want to trace 0, it does confirm that my y-intercept was -4/9. And then it comes back up and crosses at x equals 8 again. And then it just kind of rides along the asymptote. We could move it to the window further right if we wanted. So the x max, I'm going to go like 20. You can see that it comes back up, it crosses at 8, and then it just kind of rides underneath the asymptote into the sunset. So once you get a pretty good idea, you can go ahead and just copy that over. Cross your x-axis, cross your y-axis, and then it skims underneath for a second. It hits the x-axis again, and then it rides off into the sunset. The x-intercepts. Now let's say there were no holes, right? Well, let's say there was a hole at x equals 4. I'm just making this up. The way that I would graph this, I would do everything we just did, but then I would literally take my eraser, go to the x value of 4, go to my graph, erase it, and then I'll put a little hole in the graph right there. So do everything just like you normally would, and if there's a hole, just erase it and put a little hole. Okay? Any questions?